Hello! All right, we're on. That's it. That's our new intro. Normal force. Let's get normal for a second. Today's date is the 28th of the 10th. We have started chapter 2. Oops. All right, thanks guys. Listen up for me. Active listening in 3, 2, 1, 0. Anna. All right, the normal force. Now, this is a basic sort of physics concept, and I'm sure you guys have heard about it before, and I'm sure we've discussed it before. My bottle right now is not falling to Earth despite the force of gravity because of the... Right, the normal force is acting perfectly opposite the force of gravity, and that's always the case, isn't it? No, it's not. Which way does the normal force act? Right, perpendicular to the thingy, otherwise known as the surface, whatever the surface may be, okay? Now, if I tilt a desk and gravity keeps acting downwards, but my normal force is now acting sideways, what do you think happens? Things slide. They're not sliding because of gravity, they're sliding because of the normal force. It's pushing them that way. Gravity just pulls them straight down. It doesn't move them sideways at all. It's the normal force that moves things along a desk. Did you know that? If I tilted a desk, gravity's not the thing sliding it along the desk. It's just pulling straight down. Gravity has no horizontal component to it. Think about that. Right? Well, if we tilt the desk, it does, because if the desk looks like this, you don't need to draw this, my water bottle. Gravity down, normal force up. Yeah? No horizontal component. But if I tilt my desk and my water bottle's like that, then my gravity is down, my normal force is out that way, because normal forces act perpendicular to the surface. So, I have some horizontal component, and I move. Crazy, right? It's the desk that's moving the bottle along the desk. So, let's talk about normal force for a little bit. A force which acts against motion perpendicular to the surface. All right, in your heads, think to yourselves, I want you to remember two things. One, what is mass? Thank you. Yes, exactly. And the other, what is weight? All right? I want you to make sure you understand very clearly the difference between these. This is a sometimes confusing concept, but ignore what everyone else believes. Physicists know better, and weight is not your mass. They're different. So how could we sort of define mass? Mass is, who wants to have a go? We'll get a volunteer to start us off. Nicola, what was that? What? Huh? Mass? Mass? Mass is a measurement of quantity of matter? Measurement of the quantity of matter? Yeah, I'm okay with that. That's kind of a cool little explanation. I've done a terrible job of this. Quantity of matter. It doesn't really matter though. Thank you. All right, and weight is, what is weight? The what? Gravity's effect? Yeah, but it's more than that. It's a specific thing. Who knows what the units of weight are? Let's be clear about the units for mass. The SI units, of course, are kilograms. Can't forget that. Who knows what the units for weight? Newtons. Because weight is a force. Weight is the force due to gravity. Now, this language here, this due to gravity, is very intentional, okay? Weight is not the force of gravity. Gravity kind of isn't a force. Weight is, we'll talk about that later, don't worry about that for now. Weight is the force that we apply as gravity changes our direction. More complicated than that, of course, but it's a useful way to think about it, so we'll keep using it for now. Okay, so weight is the force of us or the object due to gravity. It applies a force, okay? I apply a force to this chair due to gravity's effects on me. The chair, of course, applies a force back to me. Now, in situations where, case one, and we're going to talk about these different cases a lot, in situations where surface is perpendicular to gravity, in this case, Fn perpendicular to gravity. So if gravity is acting like that, the surface is at 90 degrees to gravity, okay? Whatever this object is. Some mass we have here. Sorry. Oops. Some mass there. Surface is perpendicular to gravity. Fn is equal to negative Fg. How cool is that? They're equal and opposite forces. On one condition, who knows the condition we need for this to be true? Fn is equal and opposite to Fg. Well, let me put it this way, okay? Water bottle on my hand, force due to gravity, force due to the normal, all right? The forces are currently balanced. That means the normal force is equal to the force of gravity. Forces must be balanced, which means motion must be? What has to be constant? No, well, if acceleration is 0, yes, but acceleration has to be 0, which means velocity has to be constant, right? If I do that, then my normal force can be greater than the force due to gravity. Now, that's a bit of a stupid concept because really what I'm doing there is pushing it. It's some applied force. It's not really a normal force anymore. Generally, when we talk about a normal force, we're talking about a force that is acting to cancel out some other constant force like gravity. But it's not technically wrong to describe it as a normal force that can increase and accelerate an object. So when acceleration equals 0, that's an important point to recognize. If we're accelerating, then we can talk about the idea that one is greater than the other. This can get a bit messy. You can get down to like, analysis of the impact on atoms. Like, is your table like crumpling at the legs and so gravity's too strong and the bottle's moving downwards, right? It gets a bit weird. But generally, normal force, when they're perpendicular, we just have a situation where the forces are balanced. There's no acceleration, okay? All right, let's do an example where we calculate the force, the normal force for an object. Everyone got this down, or a little bit longer? All good? Speak now, forever hold your peace. Example 1. Find the normal force acting on this stationary block. Boop, boop, boop. Let's make it a book. It'll be a book. It doesn't really matter. Call it a block. It's going to look like a block regardless. I can draw straight lines. Twilight. No. I need it for my experiment. What? That's true. All right. Find the normal force acting on this stationary book. Now, we only know the mass, right? So how the hell are we going to find any forces? Oh, wait. What else do we know, Hannah? We also know, of course, Hannah, we know that mass equals 2 kilograms. Yeah, you're right. We do know that acceleration due to gravity, or g, is negative 9.8. But there's something else that we know about this book, not block. We know what? Stationary. We know that acceleration is 0. Okay? Yeah, cool. Yeah, thank you, Hannah. I appreciate that. I'm going to ask you the next question as well, and I'm going to keep asking you until you get a question right for me. Is that bullying? Maybe. Right? Now, there's a key concept here that we need to appreciate, all right? And that is Newton's second law, which is, of course, sum of all forces equals mass times acceleration. I think your formula and data book uses F net, not the sum of all forces. Exactly, it means the exact same thing, right? F net equals mass times acceleration. Now, let's focus on this part here, F net. What is our net force here? We have to add our forces, sum of all forces. So we've got Fn plus Fg. And that is equal to the mass of our object times by its acceleration. Okay? What is our object's acceleration? 0. So this whole side is, so therefore Fn equals negative Fg. This is where this comes from, Newton's second law. If the acceleration is 0, then this whole side becomes 0, and therefore we can subtract Fg from both sides, and we can be left with just negative Fg. Cancel on that side, we're left with Fn equals negative Fg. Everyone fine with that? A little bit of algebra? Cool? So we know that the normal force, which is what we're looking for, by the way, the normal force, is equal to the negative of the force of gravity. So what is the force due to gravity? Well, force due to gravity, Fg, is mg. Yeah, because F equals ma. The force due to gravity is just equal to the mass times its acceleration. Its acceleration due to gravity is negative 9.8. Now, this gets a bit confusing, right? Because you're like, well, a block isn't accelerating. No, you're absolutely right. We're looking at part of this system right now. So we're no longer accommodating that normal force. We're just talking about this force due to gravity. It's also related to the mass times the acceleration. If there was no other force, then gravity would make this object accelerate at negative 9.8 meters squared. So we know that our normal force is equal to the negative of 2 times by negative 9.8. And we get a positive 19 point, what is it? 6. And that makes perfect sense. It's positive, it's acting upwards. Acceleration due to gravity is negative because it's acting downwards. That's fine. Nothing too crazy in that one. Hopefully you're with me so far. Any steps you want me to explain? No? Cool. What if we're not perpendicular? Sorry, did everyone have that? Sorry. All right, we're good? Can you get it off someone else, Hannah? Here we go. Example 2. Pause. Pause. We're going to talk about case 2. Case 2, objects on an incline. And we'll get into the example a second later. And little clue, incline plane is the focus of this lesson. We're just going to be constantly comparing and contrasting over the next 2 weeks incline plane situations with flat plane situations. Now, incline means a plane at some angle to the force due to gravity, generally, okay, or the applied force, whatever it might be. So in case 2, objects on an inclined plane, we need to set some notation, okay? So use force parallel and we use this symbol for forces acting along a plane. Use force perpendicular. So a bit of notation here. And we'll use, of course, the perpendicular symbol, forces acting perpendicular, or, yeah, perpendicular to the plane. There's not really any other way I can say that. All right, 2 frames of reference we can observe this situation from. Both are valuable. One tends to be more useful than the other in most common problems we will deal with, okay? So frame of reference 1 is our usual horizontal vertical frame, okay? We'll have some theta. We'll have some object. That object will have a gravitational force acting downwards and a normal force acting perpendicular. Now, in this frame of reference, your normal force is on some angle. But generally, the angle is given at the point of the incline's elevation, right? Which is hard to match to the normal force. If you remember things like the Z rule and vertically opposite angles are equal and things like that, you can do some geometric rules and you can establish that this angle here is equal to this angle here, so then that must be equal to this angle here. Right, it gets messy, right? So generally speaking, this is less useful. And what we'll do instead is we'll imagine force due to gravity, theta, F. We're going to tilt our heads to the side to analyze most of these situations, okay? Purely because of the simplicity that gives us with that angle right there, okay? I've actually done a shocking job of drawing that, but anyway, that's all right. Okay, so we're often going to end up tilting these problems to the side so that we can imagine them a little bit easier and see what's going on a little bit better. Which means, despite it being technically wrong, and I don't love it, you will often see people talk about the horizontal component of gravity FG parallel to the plane. I might move that up the top actually, sorry, so that it's a bit clearer. FG parallel to the plane. And orange, and we'll do green. Move my FG. G. FG perpendicular to the plane. So, despite it not being technically correct, we will often talk about gravity being the force that's acting in that direction, the gravitational force parallel to the plane. Realistically, the gravitational force has no sort of horizontal motion. But if you tilt your head to the left and gravity's acting that way, then gravity's acting at an angle for you, and so it has some horizontal component. So it's all about frame of reference as well. Okay. Now, the great thing about this is the angles are a bit easier to read here. Okay, if I want to know the angle between, because essentially what I'm going to do is bring this FG2 down there, right? And I'm going to have two triangles. So this here will be FG2, FG parallel. And then I've got my triangle, and I can very clearly see that this angle here matches up with that angle there. Okay, so if I sort of rotated this 90 degrees, my right angle that used to be on this triangle here is now here. Therefore, my theta that used to be on the triangle here is now here. Okay, it's a bit of a mess with your head sort of situation, but the other thing you can also do is you can just calculate that angle, because you know that angles in a triangle add to 180. You can easily find that angle, and from that you can find that angle. But that angle will be the same as that angle. Okay. So a little bit of angle geometry here. It does get a bit messy, but you'll get so familiar with this, you'll just start doing FG sine theta, FG cos theta, and that's it. Okay, because this is going to end up being exactly the same as our parallel and our horizontal and vertical components of a vector, and it's just going to break down to FG sine theta, FG cos theta. Cos is the one that's adjacent, sine for the one that's opposite. Okay, so our angle would go here. All right. Hopefully we're following along so far. I think the best way to do this now is to actually look at an example. So we'll get straight into that. Anyone? Yep, still going? A little bit longer? All right, if you still need stuff, can you grab it off someone next to you? Example 2, for that case, find the normal force no, this one's Song of Ice and Fire. You're not allowed to read it, it's R18. That's illegal. Mass is given, it's 2 kilograms. Turns out they're the same mass, those two books. No, it's a different book. They just happen to be the same mass. Look, it looks totally different, Brendan. What are you talking about? It's very clearly a different book. Okay. So a couple of things we immediately know, all right? And let's straight away dive into them. I'm not going to redraw our diagram just yet, okay? I'm going to leave the diagram just for now. The first thing we know is we know the mass. We know it's sliding down the plane, okay? So this is not necessarily a non-accelerating object. But we do know it's not lifting up and down off the plane, and that's going to be important later on. But what we can immediately find just from that mass is force due to gravity. So we can immediately find that Fg is equal to mg, and we should straight away do that. That's going to be 2 times negative 9.8 equals 19.6 newtons. Technically a negative. We're going to assess the magnitude of this a fair bit rather than looking at that negative as a direction, because as I've sort of mentioned, we're going to imagine this gravity is being at an angle. So the idea of it having a positive or negative for direction is insufficient. We have to set some angle. So I'm just going to say equals 19.6 newtons down. But as we're going to establish again, down is not as useful right now. So we're going to change this. All right, now that we know this, I want to redraw my diagram. This time I'm going to draw just my mass, and I'm not going to draw the surface, because the surface makes things really hard to imagine. Now, our normal force is going to act directly upwards. Our gravitational force is going to act that way, and it's, of course, going to have components to it. It's going to have this downwards component, which we'll call Fg perpendicular. It's perpendicular to the plane. And it'll have this component, which we'll call Fg parallel. Sorry, that's quite tight. Is that in there? This, of course, will be the original Fg, and then we need to do our analysis of the angles, okay? Now, you can do this a bunch of different ways, all right? If we go back to our original diagram, we could imagine closing this off. There's our angle there, 30 degrees. Or is it? Right, so this is where people will make this mistake. If you try and just fit that triangle to there, you're not going to get the right answer. That triangle is now, this line here is this diagonal line here. Okay, so you have to be very careful. You have to think this through and make sure you're doing this right. No, I definitely didn't make that mistake on accident. It was on purpose to remind you guys. So the best way to analyze this then is to actually look at that angle in there. You've got your right angle there. You've got your right angle here. You've got this angle in here is going to map to that angle in there, right? And from that, you can sort of let the problem fall into place. So I like to do this 30, 90, that's 120. 120, 180 minus 120 will give me that missing angle, 60. Therefore, this angle is 60. Therefore, when I tilt like this and I see my gravity like that, I know that that's 60. Now, this is how I like to teach this. A lot of people won't do it this way. They will just teach that you've got your opposite and your adjacent, and it just becomes simple from there. So they'll actually imagine extending this out. 30 degrees is there. Oh, I don't even know how they do it, actually. That becomes the hypotenuse, I guess. Anyway, look. I don't like the way that you'll probably see your textbook do it sometimes, but essentially they just use a trick. It's a shortcut. They just say the opposite is going to be sine theta, the adjacent is going to be cos theta. I would rather you guys have an understanding and draw your second case diagram and actually make sure that you're labeling your angles and interpreting that correctly, okay? So I'll give you an exercise after this so we can practice this. But there is another way we'll look at a bit later where we just do 30 degrees and we learn this little shortcut, and you might prefer that and be comfortable just applying that as a bit of a rote learn thing. But in the meantime, we now have this diagram over here, and again, this perpendicular force of gravity, we can imagine it over here too. It doesn't matter which side we imagine it on. So we can now calculate each of them. Now, at this point, we're going to pause and we're going to go back to the original problem. What are we trying to find here? Normal force. Okay, how am I possibly going to find the normal force from any of this? So let's go back to this diagram. This is our normal force. Remember now that our gravity, what we're doing right here is we've got force of gravity and we've got Fg perpendicular, Fg parallel. Right, so this here, our Fn, this here must be equal. Fn must be equal to negative Fg perpendicular. And we know that because it says it's sliding down the surface. So it's making contact with the surface the whole way. It's not lifting up, it's not falling through it, it's on the surface the whole way. So if we look at the surface as being flat like this, we imagine that our normal force and that are canceling perfectly, so there's no vertical motion. If we're thinking about it in this angle, it becomes kind of confusing and messy. Okay, so we've got to sort of tilt our heads, look at it in this perspective. We're moving sideways, we are sliding down, and down is a bit weird in this case, but we are sliding down the surface that way. And that makes sense because look, we have this parallel component of gravity as well that's acting, and there's no friction to stop it. So of course, the object's going to move that way. It's got a force acting that way with nothing going the opposite way. So we've got these clear vertical and horizontal components now, and that's much easier to deal with. But of course, we need to go back and actually calculate them first. So let's find Fg perpendicular. Fg perpendicular is equal to Fg times by sine or cos, depending on whether it's opposite or adjacent, all right? And this is where that little trick comes in. So this triangle here, we've got Fg perpendicular over here or over here. You can imagine it either side, it doesn't matter. I don't mind which triangle you do it for, it's the same either way. But over here, Fg perpendicular is opposite our angle of 60 degrees. Also, again, 30 degrees must be tucked in there. 30 degrees must be up here. So you can imagine this as being 30 degrees. It's adjacent to 30 degrees. So if you use 30 degrees, you use cos. If you use 60 degrees, you use sine. It doesn't matter which one you use as long as you're following those rules correctly. So I'm going to solve this as 60 degrees. So I'm going to do this as the opposite. So it's going to be sine theta. So we just take our gravitational force and we multiply it by sine theta, which equals our force due to gravity we found here, 19.6. And again, we don't need that negative for this situation. It's a bit meaningless right now. We're on an angle for our force of gravity. There's no point talking about that as positive or negative. It's acting at an angle. We would have to specify that angle. And we multiply that by sine theta, which is sine of 60. Remember, we use the angle 60 here, so we're opposite our angle. We're over here, opposite the angle. And that will equal... Let's see if everyone gets it. 17. Point. 17 point what? $16?
Oh, wait, no.
Let's do two significant figures actually. 17? Yeah? Cool. That's our perpendicular force. That's equal to the negative of our normal force. Now this is where things get a little bit funky, right? We've said that our normal force is equal to the negative of Fg. That's because this is acting actually downwards. Okay, so if we imagine our frame of reference actually being on this angle, that's positive, then this down here is negative. This down here is negative. So our perpendicular gravitational force is actually downwards, which means it is actually negative. I'm not going to write down, sorry, and I shouldn't have been using that language. I'm going to say perpendicular down. Thanks. Which means negative 17 newtons is useful. And then, of course, and sorry, I'm going to do dodgy little working out here. I'm going to go and sit in a little box over here to do this last part. Our normal force, Fn, is equal to our negative of Fg perpendicular. So our normal force, negative 17, is equal to, our normal force is equal to the negative of negative 17, which is positive 17. Okay, that's a big example, and there's a couple of weird things in there, yeah? It does break your brain a little bit sometimes, and the best way to do it is to practice and figure it out. It's a bit grueling for the first one that you do, but you'll be fine after a little while. This is something that requires practice, so I'm hoping to give you a lot of time on that. Any questions about any of those steps? We can go back through any of this. I think the important thing is to be really comfortable drawing lots of diagrams for this, right? In particular, draw a diagram without the plane shown and actually label the forces with the angles, because that's one of the tricky parts that people can make mistakes on quite often. Hopefully your diagrams will be more accurately drawn to scale than mine, which is not great. That's very clearly about 45 degrees, but anyway. Anyone want me to go through one of those steps again? As an extension, I could ask you, how fast is this object accelerating along the plane? What force would dictate how fast this thing is accelerating along the plane? We're looking at this here. So along the plane, and in particular we described it as being down the plane, that's that way. We're moving that way, we're sliding that way. And in fact, we know by looking simply at this free body diagram, we know that we must be accelerating because there's an unbalanced force happening there. Oh, I hate this smartboard. No. Oh, whatever. What? I can't see now. Right, don't touch it again. So which force would be acting to accelerate us along that plane? The parallel force. The force from gravity parallel. Now, as we had our conversation before, really it's kind of the normal force that's doing things and the gravitational force that's balancing things out. That gets a bit weird. You don't need to know about that, really. But definitely in this, in the way we've drawn this free body diagram, that gravitational force that's acting along that plane like that, parallel to that plane, is going to slide that object across that plane. That sort of makes sense? So if we calculate that force, we know that the force equals mass times acceleration. We divide by the mass, we get our acceleration along that plane. I'm not going to look at an example of that today, but it's fun to think forward. Okay, so is this okay so far? Like I said, it's big and messy, and it doesn't always click until you do it for yourself. So do it for yourself. Everyone got everything they need? All right, here's your exercise. Just to mess with yous, I'm going to make it backwards. Dun, dun, dun. Just to force you to actually think about this rather than just copy exactly what I did. Which way did the plane go last time? That way. So this time, mass 3.1 kilograms. Has some acceleration. This is an object of unknown origin. Has some normal force. Has some force due to gravity. And the plane is angled 40 degrees. No, it's Pandora's box. Don't open it. Yes, it's a free body diagram. We keep objects looking simple in free body diagrams. It's good practice. All right, have a go. You haven't had a brain break yet, so of course, take a moment if you want, chill out for a second, and then we'll get stuck into this